Today I'm going to discuss interferometry and how it impacted gravitational wave detection. So interferometry is a technique that was originally developed in the 19th century, and the purpose of interferometry originally was to experimentally demonstrate the existence of luminiferous ether. So in the 19th century, it was believed that there must be some sort of substance permeating the universe. This was hypothesized due to the fact that at the time it wasn't understood how things like light and gravity could act over a distance without there being a medium. The understanding of waves was such that it required a medium such as air for sound or a musical instrument to allow these waves to be transmitted. And so this medium was considered to be the luminiferous ether. Therefore, interferometry was designed to demonstrate this. Of course, the ether was found not to be real, but the technique was developed and is still useful to this day. So the idea of interferometry is that a light beam will be split in half by a beam splitter and then sent down two arms. In the original case, these arms were perpendicular to each other. At the end of each arm is a mirror which reflects the light beam back. The beams are recombined, and then that combined beam is detected by either a detector or is simply shot onto a screen, and you can see the interference pattern. The idea behind interferometry was that a small change in the path length of the light would impact the interference pattern by constructive and destructive interference and the phase shift of the light as it has to travel a different length before it's combined and detected. Interferometry has a number of problems, largely due to the fact that it's used to measure very small things. So one of these problems is vibration mitigation. So originally, Michelson used his interferometer bolted into a university lab desk. Of course, this desk and the whole setup was vulnerable to vibrations, such as those of people walking by outside or above and below the setup. Michelson then changed the setup to try to mitigate some of these vibrations. So in his second setup, he floated the entire experiment on a pool of mercury and carried out the experiment in the basement of the university. The hope was that less of the vibration would reach the experimental setup and therefore it's less likely to disrupt the experiment. Although this 200-year-old experiment is not at all on the scale of accuracy needed at LIGO, the problems are very similar. So LIGO is of course vulnerable to vibrations, particularly seismic vibrations, and given that the accuracy with which LIGO needs to measure and the precision needed being on the order of 10 to the minus 23 meters, any vibration needs to be accounted for. The system put in place is far more complicated than floating the experiment on a pool of mercury. And there are two main methods of vibration mitigation at LIGO, first being an active and the second being a passive mitigation strategy. The active mitigation strategy involves the detection of seismic vibrations, and the whole experiment is suspended on actuators. Those actuators respond to vibrations detected in the ground, and therefore can be used to counteract those vibrations and keep the setup still. The passive vibration mitigation technique is essentially based on a pendulum. So the test masses, or the mirrors used at LIGO, are approximately 40 kilograms. And those test masses are suspended in a pendulum made up of three masses that total 360 kilograms. As such, any vibration that is transmitted into the pendulum system is largely absorbed by the other masses, and therefore a minimal amount of energy reaches the test mass, thus reducing the amount of vibration that impacts the test mass. This pendulum is supported by 0.04 millimeter silica strings, and as such, the test mass is very well isolated against seismic vibrations. Another issue that Michelson found in his initial experiment was the light source. So in order to detect any change in the interference pattern, it was important to be able to clearly delineate the various light and dark regions caused by the interference. And as such, it became important not only to isolate the whole experiment from any external light, which might blur the lines between the lighter and darker spots on the interference pattern, but also to use the correct wavelength of light and a consistent wavelength of light. So Michelson used a sodium light source. And the purpose of this is that the interference pattern is dependent on the wavelength of the light being used. As such, if you use a light source that gives off an inconsistent wavelength, then that can cause changes in the interference pattern that aren't caused by changes in the length of the arms. And so it's important to keep that very consistent. The LIGO faces similar problems with its light source. One important distinction is that at the LIGO they needed to use a megawatt laser. This is because any changes in the wavelength in the interference pattern are going to be extremely small, and thus the detection of that will be based on counting the number of individual photons that reach the detector. Using a weak laser means that very few photons actually reach the detector, and thus any change in the percentage of photons that reach the detector is going to be extremely hard to measure. And thus you need a lot of photons going through the system to detect even a small change in the percentage of photons reaching the detector at any given time, and hence the need for an extremely powerful megawatt laser. But not only does the laser have to be extremely powerful, it also has to be extremely consistent. The wavelength cannot vary at all, essentially, and so LIGO uses a system that they've developed to keep the laser wavelength to within a very small margin. Another problem that both Michelson and LIGO faced was arm length. In the initial setup, Michelson had 1.5 meter long arms, and this meant that any change in the arm length or any change caused by the ether could only act on the light for the time it takes to transmit along those 1.5 meter arms. This meant that the changes were very small, and thus increasing the arm length would increase the impact of the ether or impact the impact of the gravitational waves, and thus there would be a bigger difference of the interference pattern, and that would be easier to measure. Michelson's solution to this problem was to use a series of mirrors which would reflect the light beams back and forth until the total path length was 11 meters, which is clearly far greater than the initial 1.5 meter setup. LIGO similarly has to use a significant path length. Each arm of the LIGO, the interferometer, is 4 kilometers long, but the light itself is reflected back and forth 300 times, which means the total path length is approximately 1,200 kilometers. This is to increase the distance over which the gravitational waves affect the laser traveling through it, and thus increasing the change in the interference pattern detected at the end. All of these problems faced by LIGO were largely overcome to a point. There's only a certain amount of vibration mitigation, for example, that can be done by an interferometer on Earth. And similarly, there's a limit to how big the interferometer can be when it's confined to Earth. And as such, a new proposal has been put in place, and a project is being worked on by NASA called the LISA, which is laser interferometry space antenna. The idea being that we would launch up 3 individual satellites, each containing a laser, telescope, and test masses. And they would be sent into orbit around the Sun at the same radius as Earth, but 20 degrees behind the Earth. Each of these satellites would beam lasers to one another, where they would be reflected back. And this is useful because, obviously, being in space, the test masses aren't vulnerable to seismic vibrations. But also, being in space and through the use of 3 separate satellites, it's possible to make the path length essentially as big as you want. The proposal for LISA is 2.5 million kilometers long. It's not without flaws though, so LISA is uniquely vulnerable to solar radiation and solar winds, which can disrupt the test masses, which is not a significant problem on Earth due to the enclosure and due to our atmosphere. A solution to this problem is the use of zero-drag satellites. The idea behind these satellites is that the test masses are not actually connected to the satellite. They're essentially in free fall within the satellite. The outer shell of the satellite is still going to be vulnerable to solar winds and solar radiation. However, because the test masses are not connected, they are shielded from these effects. The outer shell is then, the distance between the outer shell and the test masses are then measured, and any change can be mitigated by thrusters on the outer shell, thus keeping the orbit stable. This opens the door to a significant improvement in our ability to detect gravitational waves, and due to the much bigger setup and the much lower vulnerability to vibrations, we can hope to measure events caused by things smaller than were required to be measured at LIGO, and much further than can ever be measured by any interferometer on Earth.